Hi, everyone. In this video, we will talk about our paper, Coresets for minimum enclosing balls over sliding windows. Coresets are important tools for big data analysis. By reducing the data size via coresets, many computationally intensive algorithms can scale to large datasets with little loss of accuracy. Coresets have been studied for several basic problems in machine learning, such as k-means clustering and subspace approximation. Coreset for minimum enclosing ball, or MEB for short, has also received significant attention. For a point set P, its MEB is the smallest ball that contains all points in P. A subset is a coreset of P if it can approximate the radius of the MEB of P within a bounded error. Coreset for MEB is useful for a wide range of applications. For example, coresets for MEB can be used to train support vector machines. It has been proven that many kernel methods, including SVM, are equivalent to minimum enclosing balls in reproducing kernel Hilbert spaces with feature transformation. So, we can speed up SVM training on large datasets by restricting the work sets to small coresets with theoretical guarantees. As another example, coresets for MEB can be applied to approximate furthest neighbor search. For any query point, its furthest neighbor retrieved from the coreset can approximate the exact one from the original dataset, with a theoretical guarantee. Existing work on coresets for MEB focuses on the batch or append-only streaming setting. But their algorithms cannot be used for sliding windows. So, we study the problem of coreset maintenance over the sliding window that is continuously updated in a data stream. Specifically, given a window size n, we always maintain a coreset for MEB with respect to the latest endpoints in the stream. We propose the first algorithms to maintain coresets for MEB in the sliding window model. Our algorithms are theoretically sound since they can guarantee constant approximation ratios with sublinear complexities. They also show good performance in experimental evaluations. They can achieve up to 4 orders of magnitude speedups over state-of-the-art batch algorithms. Meanwhile, their results are of high quality, with less than 1% relative errors compared with the optimal ones. The full version and implementations of this paper are available on the given URLs. Thank you for your attention.